Let's have a look at this word problem. It says here, where you attach a loonie and a dime, there's a loonie and there's a dime, at the ends of a thread, there's a thread. You put the thread over a smooth horizontal bar and add a pulley, there's a pulley on it. Finally, you release your hands and the loonie is going to drop down and the dime is going to go up. Ignore any friction. You can determine the magnitude of the acceleration. When I do this particular word problem, I'm going to turn the lights back on for a moment. When I do that particular word problem, in the past, students have always asked me, oh, maybe I'll go back the other way. Students have asked me, because I have a pulley here, okay, does that pulley amplify the force? Does it do mechanical advantage having this pulley here? It's a good, valid question. You guys are all in mechanical engineering. I'm sure you've seen this kind of question before. The answer is, in this scenario, no. What the individuals who asked me in the past, that I'm just taking advantage of those questions, is they're thinking of this scenario here. You notice here they got 1, 2, 3, 4 pulleys. In this case, you do have mechanical advantage because of the pulleys, not in this scenario. Over here, if you look at it, we have 1, 2, 3, 4. So the mechanical advantage here is 4 times. If I were to apply a force here, what is actually being applied to the weight will be 4 times my force because of mechanical advantage. I will leave that to a future class for you to solve this one. In my case right here, this is all we're interested in as far as Newton's second law of motion goes. There is no mechanical advantage by having 1 pulley. I'm going to do a demonstration of that. So I went into my workshop and I come up with this. This is a clothesline pulley. I had a rope, and I have a woodworking shop, so I cut a 2x4. They're not exactly the same weights, but they're close enough for what I'm trying to do here. So I have two weights. In my case, they're the same. I'm going to change up that in a moment. And here's my pulley. And it's supposed to be a frictionless system. If I shake it a little bit, it shouldn't really move any. It ought to be the same because they have the same weight. So the weight force on this side right here is equal to the weight force on that side. The two are balanced. There's no mechanical advantage here like they would have in this scenario right here. Now if I were to, the question here ought to say as well as massless rope. It should have a massless string, so don't include the mass. Let me show you what happens if I do have a mass. I'm going to change this a little bit. And let's see if this works for me. Come on. No, it works for me when I did it before, but no, not today. There we go. Notice what I've done here is I've just changed the mass a little bit on this side. What I've done is I added more rope on the left side, increasing the mass on my left here. The mass is the same. The length of the rope and the length of the rope plus the two wooden pieces there have the same mass. But if I were to change this, now I've got this extra mass of rope here, and if this works, it goes down because the weight here on the left-hand side is greater. So the question normally has use a massless string or massless rope. Okay. Now I also have an additional weight. I'm going to put an additional weight on one side. Per our lecture in the past, I said the direction the object is moving, you are to make that the positive direction for our vectors. So I have a weight here. I'm just going to lift this up. Obviously, it's going to go its way down. So which direction is positive? Looking at this side, this half right here. Going down is positive. Going down is positive, and this one is going up. So on this half of this pulley system, up is positive. On my left-hand side of the pulley system, down is positive. So what exactly is this pulley doing? It's not giving any mechanical advantage whatsoever. All it's doing is changing the direction of the force. If I were to put a marker here, it's just changing the direction of the force. I'm going to put a mark on, I waxed these, I don't know if the mark's going to go on here. I'm going to put a blue mark here. If we follow that blue mark, we'll see what the pulley is actually doing. Okay, I think I got it this way. Can you see that mark? So it's going up here. The weight on my left is going down, the weight on my right is going up. Let's see what's actually happening as far as the mark goes. So the mark was going up here, so the force was going up around the pulley, and then it went back down. So it followed the complete path, up and down. So all this pulley does is change the direction of the force. There's the blue mark. So it's going to change the direction of the force. Even though I say up is here, eventually it's going to come back down for our mathematics. Now we'll show you how that works momentarily. So the pulley just changes the direction of the force. Now in order for us to solve our problems, what do we have here? This is a weight force. And I call it weight force for a reason. This is also a weight force. So if that's a force and this is a force, it'll be the same as my doing this. You're doing a tug of war. Somebody's pulling in that direction, another one is pulling in that direction. That is exactly what's happening here with this pulley. Except that it's vertical, but if I were to stretch it out, force that way, force this way, the greater the force on that side is going to start moving everything that way. So in order to solve our problem, we're going to stretch it out into the x-axis, take it away from the y-axis. It's the exact same thing. We could solve it here using tension in the wires, and I'm going to take a shortcut. Okay. So this has a greater force going that way, this is less force. I'm going to stretch it out in the x direction, and we'll use the sum of the forces in the x direction is equal to mass times acceleration in the x direction, just to simplify the word problem.